Hello my dear students, I hope your preparation is going well and I welcome you to our NEET World channel. So today we will be discussing the PYQs of EAPCET again. Okay, so here the first question is from aldehydes, ketones, carboxylic acids. So look at here, the styrene upon treating with KMnO4 followed by acidic hydrolysis gives X. Again upon treating with bromine in FeBr3 we will get Y. So what is this X and Y in the given reaction they are asking. So simple it is. Look at here, what is the starting material? Styrene, right? What is the structure of styrene first? Yeah. So look at here, take styrene first. So styrene will be like this. So on phenyl ring you put CH double bond CH2, this will be the styrene. Okay, so whenever you treat this with KMnO4, what happens here? So KMnO4 breaks these bonds and oxidizes this compound completely. Okay, therefore you are going to get your X as carboxylic acid followed by acidic hydrolysis there now. So this gives you carboxylic acid like benzoic acid here, and this is also one more carboxylic acid, that is formic acid or CO2 gas will be liberated here. Okay, so we are not bothering about this because in the options only phenyl derivatives are there, like phenyl group with benzoic like carboxylic acid. So benzoic acid I can say. Okay, so this upon again treating with, this is our X. So this upon treating with Br2 FeBr3. So FeBr3, whenever we add Br2 to this FeBr3, it will generate a carbocation. So what is a carbo like electrophile I can say. Okay, so here we do not have like alkyl halides, we have only bromine now. So we are going to get a bromine like charge on like positive charge on bromine. Okay, and one of the bromide ion will be taken by this and we are going to get FeBr4 minus. Okay, so these are the two species formed here. So bromonium ion here, Br plus 3, which is electrophile here, that will be attached the given X compound here. So where it goes, this electrophile goes on this benzoic acid at meta position here. So why at meta position? Why not at ortho and para position? Because what is the nature of this carboxylic acid group? So it is electron withdrawing group now. So electron withdrawing groups direct the incoming electrophile to the meta position, because the electron withdrawing groups decreases electron density at ortho and para position and creates partial positive charges. So relatively more electron density is present at this meta position, therefore electrophile is directed to the meta position, because electrophile is also electron deficient species now. So again in the substrate also we have electron deficiency at ortho and para position. So what is a relatively more electron density containing position? That is meta. That's why bromine positive charge, bromonium ion is going to the meta position. That's it. That will be the concept you should know here. Okay, and next, what is the option here we can go with? So see, option number C, we have benzoic acid and also meta substituted compound here. So this is our X and Y. So option 3 will be your answer for this question, right? Yeah, let us move forward with few more questions. Look at here, try to solve this question. So try to solve this question. If the standard enthalpy change delta H reaction for H2 Br2 gives rise to 2 bromine is minus 72.8 kilojoule. Okay, the standard enthalpy of formation. Okay, the standard enthalpy of formation of HBr they are saying. See what they have given, H2 plus Br2 gives rise to 2HBr. Okay, so 2HBr. So for this delta H reaction, so delta H reaction is given as, the enthalpy change for the reaction is given as minus 72.8. Okay, minus 72.8. So this is enthalpy of reaction. Now what they are asking, standard enthalpy of formation. So whenever you are writing for standard enthalpy of formation, see this is the value for this reaction. Whenever we are writing for enthalpy of formation of a particular product, always you should get a product of 1 mole. The amount of energy absorbed or released when 1 mole of product is formed is called its standard enthalpy of formation. That's it. So it means this is how many moles it is forming, 2 moles, but what I am saying, we require only 1 mole. It means what you should do, you should divide this equation with by 2, and this value also will be by 2. Therefore you are going to get half H2 plus half Br2 gives rise to 1 HBr. See, now in this particular reaction we are going to get a 1 mole of our product HBr. So now in this reaction, whatever the enthalpy change is there, that will be called as enthalpy of formation of HBr. So same reaction, but what we did, just we divided by 2. So the value will be also same, but divided by 2, so that you will get the exact answer. So minus for this, how much it is? So divide this number by 2. Enthalpy of formation, enthalpy change for the reaction H2 plus gives rise to this much. Okay, enthalpy of formation. So will be how much now? So take this 72.8 divided by 2, so that you are going to get 36.4. Yeah. So this will be your answer for the question, right? Yeah. So let us move forward. Next, tell me the number of spectral lines observed when 1 electron returns from 6th shell to the 2nd shell in the hydrogen atom is. So very easy now. So number of spectral lines, how you can say this? So just use this formula, N2 minus N1 plus 1 into N2 minus N1. Okay. So how we are getting this formula? So otherwise you, by 2, this equation by 2. So how you are getting this? So just if you want, you just take like this, number of spectral lines, like n equals to 6 to n equals to 1 they are saying now. 6, this is 5, 4, 3, 2. So they are saying second shell. Yes, from here. So from, we can expect electron from 6 to 2 like this, or 6 to 3, or again 3 to 1, and 6 to 4, and 4 to 3, okay, like this, or directly 4 to 2 like this. So write all the possible lines and you are going to get a number. So just divide that, just count that number of lines you are going to get, that will be your answer, or use this formula so that you will get any one of the option. Okay, so just tell me, try and tell me your option for your answer for this particular question in the comment box. Anyone in the chat box can answer? Yeah, I am looking into the chat box, please tell me. Yeah, anyone in the chat box? Yes, just answer this question in the comment box. Okay, next here, the approximate ratio of speed of light in vacuum to that of an electron in the first Bohr orbit of hydrogen atom is. See, what is the speed of light? Speed of light in vacuum is 3 into 10 power 8 meter per second right now. So this is for light, speed of light. So I am taking VC. Okay, velocity of light. Okay, next, now what they are asking, velocity of electron in hydrogen atom. In hydrogen atom will be, what is the formula we have? 2.18 into 10 power 6 meter per Z by N meter per second right now. So now for first Bohr orbit of hydrogen means Z value, hydrogen atomic number is 1, first means N value is also 1. So this is the velocity of first Bohr orbit of electron in the first Bohr orbit of hydrogen. So ratio of these two they are saying, the approximate ratio of these two things they are asking. Okay, so what we are going to get, see, if you divide these two numbers, so this will be 100 you have. Okay, so you are going to get around 300 by 2.18. Okay, so this is what Vc by V, velocity of electron in the first Bohr orbit of hydrogen. So if you cut this, you are going to get around 137 times. Okay, so velocity of light to the velocity of electron in the first Bohr orbit is 137 by 1 time. Okay, this is the ratio, approximate ratio. So your option number B will be your perfect answer for this question, right? Yes. Let us move forward. Yeah, so tell me again, here we have one more question. X and Y in the following reactions are. So look at here, very important this is. See, given carboxylic acid, upon treating with B2H6 followed by hydrolysis, we are going to get X this. So what is X here? So just B2H6. What is the use of B2H6 here? So it will be reducing, acting as a reducing agent and reduces carboxylic acid to respect to alcohol. So what is the respect to alcohol? Something like this. Okay, so here it will turns into CH2OH. This is a X compound here. So B2H6 is a reducing agent, reduces carboxylic acid to respect to alcohol. So what is our X here? So this is benzyl alcohol here and here. Either A or B is our answer. Okay. Next here, if you look, carboxylic acid treated with thionyl chloride. So whenever you treat this with SOCl2, you are going to get benzyl halogenation here. So benzoyl chloride will be formed here. Benzoyl chloride is formed. So these upon treating with H2PDBaSO4. So what is this H2PDBaSO4? This is the Lindlar's catalyst. We call it as Rosenman reduction. So what happens here is this halogen is there now, that will be removed and placed with one hydrogen. So aldehyde formation takes place. Okay, so try to remember acid halides upon treating with the Lindlar's catalyst, we are going to get aldehydes. Okay, this is also important reaction. Okay, so named reaction again it is. So this conversion is also important, just try to remember. So what is our Y? So Y is our aldehyde and X is our alcohol. So where is our Y here? Aldehyde. Yeah, so aldehyde and alcohol. So your option number B will be a perfect answer here, right now? Right. So let us move forward with few more examples. Yeah, so here identify the major product from the following reaction sequence. See, we have a alcohol, okay, treating with PCC, pyridinium dichlorochromate. Okay, so what happens here? So PCC oxidizes. It is a good oxidizing agent, I mean for primary alcohols to conversion of primary alcohols to aldehydes. This is the best reagent you can use here. Okay, so that you are going to get a aldehyde group here. So like carbon which is attached to the alcohol is converted into respect to aldehyde. Okay, like this. Okay, these upon treating with Tollens reagent. See, here we are using PCC, particularly PCC converts primary alcohols to aldehydes. If you use any other oxidizing agents like KMnO4 or anything, Jones reagent, anything that converts these primary alcohol to respect to carboxylic acid, like further oxidation takes place, but this is a controlled oxidation, gives this aldehydic product. Okay, upon treating with Tollens reagent, converts this alcohol like this aldehyde to carboxylic acid. See, Tollens reagent is given by all types of aldehydes right now. So it means aldehydes are oxidized to respect to carboxylic acid. So write this species as it is. Okay, like this. Okay, like this. So now this 5-member ring again treated with bromine and red phosphorus. See, this is called HVZ reaction. What is the name of that reaction? I am saying HVZ reaction. In HVZ reaction, see the alpha position of the carboxylic acid group. See, this is the alpha position of the carboxylic acid group now. See, this is the carboxylic acid. The adjacent carbon is called alpha carbon, right? So if any hydrogen is present, that one hydrogen from the alpha position will be converted into like halogenation, like bromine, chlorine. Here bromine is there now, so that will be replaced or substituted by bromine here. So alpha halogenation takes place like this, Br, so COOH, like this. Okay, so this is the product formed in this reaction. So where do we have this kind of product? See, option A having the suitable answer like this. As per the option, so option A will be your answer for this question, right? Sir, H3O, which reagent is this, sir? So H3O plus means just acid hydrolysis. So for example, look at here, when I used this aldehyde conversion to carboxylic acid. So what happened here? Whenever we have aldehyde conversion to carboxylic acid, see, first of all, the Tollens reagent makes a salt. It forms a salt like this. Okay, so after formation of this salt, if we hydrolyze this with acid hydrolysis, we are going to get a carboxylic acid like this. Like this. So what is the use of H3O plus? So it is a acidic hydrolysis. I hope it is clear. Those who are asking in the comment box, KR physics. Yes. Next. So will you able to solve this question? So look at this. For a certain chemical reaction, for a certain reaction at 300 Kelvin, K is 10 and delta G naught for the reaction is. So what is this? Tell me. What is this? Tell me. What is the like how can we approach this? So what is the reaction relation between delta G naught and K equilibrium? So delta G naught equals to minus RT ln K right now. So K means here K equilibrium. Okay, equilibrium constant. So you can write this as 2.303 RT log K. Okay, so this is delta G naught. Okay, so now just substitute 2.303. What is the R value we want? Answer should be in kilojoules. So take this 8.314. R is 8.314 into 10 power minus 3 kilojoule per mole into temperature is how much they mentioned? So this is 300 Kelvin. So take here 300 Kelvin. Okay, Kelvin into log K. Log K is how much? Log 10 is how much? 1. Right now, so this value is 1 into. So here I can write this as 0.3 into 8.314 into 2.303. This is equals to delta Z naught right now. So delta G naught will be, see, look at here, 2.303 into 8.314 will be giving us around 19.1, okay, into 0.3 kilojoule we have, kilojoule per mole we have. Okay, so now 19 3 is a 57, right? So you can write 3.75. Okay, okay, here one decimal and another decimal, so you are going to get 5.73 kilojoule per mole as your answer. Okay, so the nearest numerical, nearest integer is what? I can say it as a 6, minus 6 kilojoules you can write here. If they are asking for nearest integer or whatever the way they are asking, just put the value over there. Okay, that will be your answer, right? Yes. So someone asking, sir, then how to use OH and CH2OH? Where exactly, in what reaction you are asking? I just wanted to know specifically. You mentioned like what kind of reaction you are asking for. Okay, so yeah, so based on your doubt, I just wanted to ask you one question here. See, remember, whenever you have primary alcohol, so this is a primary alcohol now. So if you oxidize this, there are two chances of formations. One is either aldehyde. See, primary alcohol means carbon, the OH group is attached to the carbon which is directly attached with only one carbon. Right now this is like a CH2 group right now, so these are called primary carbons. So you can able to get two type of products here depending upon the reagent you are using. So one is aldehyde, okay, partial hydrogenation, like partial oxidation takes place to give aldehydes. Like here the suitable reagent is what? PCC, which we have discussed. Okay, so instead of using this, if you use KMnO4 or K2Cr2O7 or Jones reagent, like this, if you use, you are going to get something like this. Your answer will be like this. So this is a carboxylic acid formed when you are using the strong oxidizing agents. Okay, yeah. So now if we have ketone, if we have secondary alcohol, see, same number of carbons I am writing, but I am keeping this OH group at the second carbon. So here it is at first carbon. So this carbon attached to this side one carbon, another carbon is this side. So two carbons are attached, so it is a secondary carbon right now. So if you use any of these oxidizing agents here, you are going to get a ketone here. So there is no chance for carboxylic acid, whether it is strong oxidizing agent or a weak. So it will always be giving ketones as your answers, but not as carboxylic acid, as we seen in the first question. Okay, yeah. So I hope your doubt is clear in this thing. Yeah. I hope it is clear now. KR physics in the chat box. So let us move forward with few more questions. So look at this, the solubility KSP question we have here. The solubility of AgBr having solubility product is this much. This is a solubility product in 0.2 molar NaBr solution equals to. So they are asking solubility of AgBr in the 0.2 molar NaBr. See, AgBr is a sparingly soluble salt. AgBr is a sparingly soluble salt. So it means whenever you place this in the aqueous medium, it will dissociate or it will soluble only to small extent, okay, and you are going to get this kind of ions, okay. Now to this equilibrium we are adding NaBr. So what happens when you add NaBr? NaBr is a strong electrolyte now, so you are going to get Na plus Br minus ions, okay. So due to the presence of this strong electrolyte along with this weak electrolyte, the concentration of bromide ions is very high due to the NaBr. So therefore, since the concentration of NaBr minus is more here, bromide ion is more, the equilibrium favors backward, because if concentration of products are more, it favors backside. This is called Lee-Chatterjee principle, okay. So now always remember, equilibrium should be maintained. If the concentration of product is increased, equilibrium goes backward. If concentration of reactant is increased, equilibrium moves forward. See, due to the presence of this common ion from the strong electrolyte, bromide ion concentration is raised, therefore equilibrium goes backward, right now. So now what happens to the resultant solubility then? So what is the concentration of AgBr, like Ag plus ion in the resultant solution when we have NaBr? So for that you just use solubility product will be equals to concentration of Ag plus ion and concentration of Br minus ion, okay. So now concentration of Ag plus ion we need to find when in the presence of bromide ion. So I just want to find solubility or concentration of this Ag plus ion, which I am indicating as S. And what is solubility product here? 5 into 10 power minus 10. And what is the concentration of Br minus ion? So you have Br minus ion concentration is 0.2 from this NaBr, and we don't know here now, let us say S. But when you compare this 0.2 plus S, the concentration of bromide ion from this weak electrolyte is almost negligible, because equilibrium is going backward. Therefore this will be around 0.2 only, that is concentration coming from strong electrolyte only. So just take here 0.2. So what is your S here? So your S will be 5 into 10 power minus 10 by 0.2, right now. So you can write these as like 50 here, 2 here, right now. So this will be how much? 25. So 25 into 10 power minus 10 will be your answer. So your option B will be your answer for this question. Yeah. So anyways, so we have a live session at evening also. Someone is saying, sir, you please keep live in the evening, sir. Yeah. See, like every day, Monday, Tuesday, Wednesday, I will be taking live at the evening sessions also at 5:30. I will be taking. Okay. So if you are new to this channel, first of all, click on the like button and do not forget to subscribe this and join our evening classes also. Okay. Yeah. And if you want to join with us, you just contact to the mobile numbers given in the description box. Okay. Yes. Next. So take these questions as a homework and try to practice them, try to answer them. If you are really facing difficult, just watch the previous live session that I have made on this particular topics. Okay. So where I have discussed, especially from last few days, I am covering all the EAPCET, exclusive EAPCET sessions are taken by me here. Okay. Now for few days, so just utilize this classes properly. So just practice this PYQs from thermodynamics here I have, okay, and equilibrium here I have from ionic equilibrium, and again from hydrocarbons here I have one question. So try to do this PYQs. If you are unable to do this, just go to the previous live sessions I have made. Okay. Yes. Yeah. Try this equilibrium questions, and this is from amines chapter. Like this, you just keep on trying. If you are facing difficulties, just watch the previous live sessions, or directly you can ask me in the chat box, or you can join our Telegram group. Okay. And you can post the doubts there. We and our team will be there to address your doubts. Okay, so thank you for watching. Stay connected with this channel and make your preparation to the next level. Thank you.